Hi everyone. So this is week 5 going on. So we will solve the previous year's week 5 assignment. Okay. And hello, welcome to my session. Let's start. So today, with the help of my session, we will try to understand magnostatic field, how the source of magnostatic field, or what are the boundary conditions, and what are the characteristics of diamagnetic material, and these kind of and similar more concepts we will try to understand. Okay, so let's start. Okay, so the first question here is, which one of the following is not a source of magnostatic fields? Okay, so first let's understand what is magnostatic field. So magnostatic field, it has it you can understand by its name only that at this is these magnostatic fields are those magnetic fields which at any given point its magnitude and direction will remain the same. So this kind of magnostatic field is known as magnostatic fields. Alright, so can someone of you tell me which one of the following is not a source of magnostatic field? One second. Sorry guys, I was not able to hear you. Yeah. Hello ma'am. Hi, go ahead. Ma'am, your voice is not audible ma'am. Oh, so sorry. Yeah, now I get it. It was connected to my headphone, so you guys might not have. Sorry about that. So yeah, so I was talking about magnostatic fields. So what is which one of the following is not a source of magnostatic field? That's what the question is. And to understand what is magnostatic field here, magnostatic field, from the name itself you can understand what magnostatic field means. So magnostatic fields are those fields which at any given point its magnitude and direction will remain the same. So magnostatic means कि magnetic field will be constant throughout the time. So it won't change, and its magnitude won't change, its direction won't change. Okay. So can someone out from you tell me which one of the following is not a source of magnostatic field? A DC current in a wire, a permanent magnet, an accelerated charge, an electric field linearly changing with time. Can someone tell me कौन सा इनमें से मैग्नोस्टैटिक फील्ड का which one? Yes. Mm-hmm. So a DC current in a wire will produce what? Will produce a DC current in a wire. Yes. So I am here. The question is, which of the following is not a source of magnostatic field? Okay. Okay, so let's go into it. So Biot-Savart's law says that B vector is equals to mu naught, that is magnetic field, is equals to mu naught upon 4 pi I dl cross r. If we are going for magnetic field due to a point charge q which is moving with velocity v, then the magnetic field will be mu naught upon 4 pi q v cross r upon r square. Okay. Now we know what will be the magnetic field due to a moving point charge q. Now, one second. Yeah. So now if let's say this the charge which has a velocity v, now let's say if this velocity itself is changing, that is, it means that it is a accelerated charge. Accelerated charge means that the charge, let's say q itself is moving, okay, with v, right? This charge is moving with v, and it has this, okay, one second, it's not working. V, and this v itself is changing with time, so it has acceleration a. Oh, sorry. Yeah. So v itself is, so here let's say v is dependent on t, then b will also be, this b will also be dependent on t. So this means that for accelerated charge b depends on t. So here b due to accelerated charge will not be magnostatic. Other options here have a magnetic field, but all these magnetic fields are static in nature. That means that at any given point their magnitude and direction will be same. But magnetic field due to accelerated charge will have a dynamic magnetic field. That means it will be changing with time. Okay. Is there any problem in this question? Okay, okay. Let's go ahead. Okay, so the option here is, let's go ahead. Okay, question 2. Plane z is equals to 0 and z is equals to, yeah, hello. No, no, here it's not about magnetic field. It's about magnostatic field. Hello? Once. Yeah. So, yes, yes. Magnetostatic magnetic field means that the magnetic field won't w- uh, mag- magnetic field won't be changing its magnitude and direction with time. So once, are you getting? So magnetic field, um okay. um okay, so magnetic field can change with time, okay, can change, and remain same. So those magnetic fields which remain same, whose magnitude and direction remains same for a given point, then it will be known as magnostatic field. Okay. But if this magnetic field is changing with time, then it won't be called as magnostatic field. It will have a dynamic nature. That means it will be changing with time. Okay. So here DC current will produce magnetic field, but it will be magnostatic. A permanent magnet will produce magnetic field, but that magnetic field will also be magnetostatic. Electric field linearly changing with time will also produce magnetic field, but that magnetic field will also be magnetostatic. Only an accelerated charge will produce magnetic field, which won't be static in nature. Okay. Okay, so let's go on question number 2. So plane Z is equals to 0 and Z is equals to 4 carry current K equals to minus 10 AX ampere per meters and K equal to plus 10 AX ampere per meter respectively. The direction of H at the point 1, 1, 1 is. Okay, so this question here is saying that there are two planes. Okay, Z is equals to 0 plane and Z is equals to 4 plane. The first plane has a current density of minus 10 AX amperes per meter. Okay, the first plane, that is Z is equals to 0. The second plane, that is Z is equals to 4, has a current density of 10 AX ampere per meters. Okay, now it's asking the direction of H at the point 1, 1. तो सिंपल क्वेश्चन है, इसमें दो प्लेन दिया हुआ है विद डिफरेंट दो प्लेन दिया हुआ है, अलग अलग करंट डेंसिटी दे रखी है और हमसे डायरेक्शन ऑफ एच पूछा है 1,1,1 पे. ठीक, तो पहले हम इसका वो देख लेते हैं. ठीक, चलो. सो मैग्नेटिक फील्ड ड्यू टू करंट शीट. ठीक, तो एक we have it here. I have given a figure to you. Okay, with a plane. Okay, so in the figure alongside the sheet lies along the xy plane. Xy plane means in the z direction. Okay, and it carries a current K is equals to KR in the x direction. Okay, K is a surface current density. So using the right hand, one second. Yeah. Now let's use the right hand rule and the symmetry of the problem. So here the sheet is infinitely long, isn't it? For Z is equals to 0. So using the right hand rule and the symmetry of the problem, we can find out the field in the region, isn't it? So first reason is Z greater than 0. Okay, and the second reason is Z greater than 0. Okay, so let's say the current is going in this sheet. Okay, in this sheet the current is flowing in the positive x direction. Okay, alright, and the reason here is either Z greater than 0. One second, let me try using my back on. Z greater than 0 or Z less than 0. Okay, so these are the two regions given to us. So now let's try to find the field, direction of the field. Okay, so the direction of the field for here the current is in this sheet, the current is flowing in the positive x direction. Okay, and then for the Z greater than 0, using the right hand rule, okay, we will find out that our magnetic field is in minus y direction. Okay, similarly for the reason Z less than 0, using the right hand rule for Z less than 0 reason, and we here the current is flowing in the positive x direction, using right hand thumb rule we will find out that the magnetic field is in plus y direction. Okay, now let's go to find out the magnitude of the field. Okay, so the magnitude of the field will be, let's use Ampere's law. I hope you know Ampere's law. Ampere's law says that B dot dl for a closed curve will be mu naught I enclosed. Okay, this is the Ampere's law. Do you have any problem till here? So first what we did is we find out the direction of the magnetic field, and then we are trying to find out the magnitude of the field. Okay, and then we will find out the direction of H later on when we will find out the magnitude and the direction, and then we will go for the direction of H. Okay, so now here we have made a closed loop. Okay, on this sheet we have perpendicular to this sheet we are making a closed loop. Okay, so now we choose this C, that is this the closed surface, closed loop that I was talking about. So let's choose this C as a rectangle of length L. Okay, which cuts the plane perpendicularly. So this, it is cutting the plane perpendicularly. Okay, so thus B dot dl will be, B dot dl will be 2 dot dl. I will tell you why. It's this because for this reason it is perpendicular, and for this reason it's perpendicular. Let's say it's L, 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 L. Okay. So only for this reason and for this reason, which is parallel, the other components will be 0. Okay. For the vertical component it will be 0 since it will be perpendicular for B dot dl. Okay. And for the parallel components will be BL plus BL. So for a closed loop it will be B dot DL, it will be equal to 2 dot BL. Okay. Mu naught I enclosed will be equal to mu naught KL. I enclosed will be, total will be K, that is current density, into the length, that is L, total L. Okay. So 2 BL will be equal to mu naught KL. Okay. So putting this to this side, which will be equal to B equal to mu naught K by 2. Okay. So now this is the magnitude of the magnetic field. Problem till here? Okay. Alright. Now, so I have already discussed with you, for Z greater than 0 region, it has a direction of negative Y. The magnetic field was in negative direction. So let's put the whole vector together, whole magnetic field vector together. That means the magnitude as well as the direction. So for the first reason it will be minus mu naught K by 2 Y vector. For Z less than 0 it will be plus mu naught K by 2 Y vector. Okay. Alright. So here this magnitude is independent of XYZ coordinates. Okay. Till here it's understood. So we tried to find out the formula what we can put here in the form of sheets. Sorry, when the sheets are given to us, we have found out the formulas, and only now we have to put the coordinates and we will be able to find out what will be the value. Okay, so we have found out the magnitude and the direction, whole vector we have found out, formula we have found out, and we will be solving it according to the question now. Okay, so two sheets were given to us. One sheet was given at Z is equals to 0 and another sheet was given to us at Z is equals to 4. Okay, the first one was saying that the current density was in negative x direction, that is minus 10x, x cap. Okay, and the second sheet has plus 10x current density. So both of these sheets have opposite current density, opposite direction. It is in opposite direction. Okay, this is given in the problem. Okay, so the first problem is, in the given problem, point P, that is equals to 1 comma 1 comma 1, field due to sheet at Z is equals to 0 will be B1 minus mu naught K1 upon 2. Put the K1 value. Now find out the field due to the sheet at Z is equals to 4. That is B2 plus mu naught K2 by Z. Put the value of K2, that is 10x. Overall field will be B is equals to B1 plus B2. So here mu naught is not given to us, K1 is given to us, that is 10x. Put it there by 2, it will be equals to how much? 5 mu naught, isn't it? 5 mu naught. Yeah, go ahead. Haha. Haha. So what are you talking? It's a yeah. So we don't need to take that much. We only needed to tell here. We only need to tell the direction. We don't need to calculate the whole value. So when it's needed, we will put the value of mu naught. If it's not required, we don't need. It's only here. It's only the direction is asked. Okay. Okay. So here it's a 5 mu naught. For second also put the K2, we will get it's 5 mu naught in the y direction. So total overall field will be equal to B1 plus B2. It will be equal to 10 mu naught. So H will be how much? Here B is equals to mu naught H. So H is equals to B upon mu naught. So H will be equals to 10 in direction of y, positive y. Okay. So here answer will be the direction of H at point 1 comma 1 comma 1 is y direction. Okay. Huh? Huh? Yes. See. Yeah, it's minus mu naught k by 2, right? So, but our k1 is itself is negative. So negative negative becomes positive. Okay. Yeah. Now the second question is find the direction of value h at 0 comma minus 3 comma 10. So 0 comma minus 3 comma 10. See, point P1 is in between the sheets because it was 1 comma 1 comma 1. The second point is at 0 comma minus 3 comma 10. So since it has a z is equals to 10 value, it will be above these two sheets. The point will be above these two sheets, right? Is there any problem in understanding the position of these 2 points? Okay. So it is asking us what will be the direction of H. So again, B1 we know the formula. Put the value, so minus mu naught K1 by 2. We know the formula for K1. We know the value of K1. We will put it. That is 5 mu naught Y. For B2, it will be equals to minus mu naught K2 by 2. Okay. Because it's outside the point. The point is outside. We will use the right hand thumb rule and when we will use the right hand thumb rule, we will find out that it's in the negative y direction. So again, it will become B2 will become minus mu naught K2 by 2. So putting the value of K2 here, it will be again minus 5 mu naught Y. Then we will we will sum it, sum B1 and B2. That will be our total B, which will be equals to B1 plus B2, 5 mu naught plus minus of 5 mu naught, which will be equals to 0. So our H will be equals to 0. Alright? Yeah. Okay. So here, see. So first point is given in between these two sheets. Okay. So when we will find out the uh, the direction of the magnetic field, we will use right hand thumb rule. Okay. So for z greater than 0, when we will find out, it will be negative y direction. For z less than 0, it will be positive y direction for this point. Okay. Ha, got it? Now, yes. So now when we will go outside this magnetic, outside these two sheets, for the first one it will be similar. Right? See, um, let's see that if my background works or not. See, for this sheet is here, okay. For z greater than 0, it had a negative y direction. Our B was negative y direction. For z greater than 0, it had a positive y direction. Okay. Similarly, for this sheet, it will have a, for this, it will have a the current is in negative direction. Current is in, now since look at the direction of the current density. It is opposite, right? So here for this sheet, this whole sheet, the direction of the magnetic field here will be in this direction, right? And above this sheet it will have a direction of this sheet side, right? Okay. So now okay, so here we will see that in between these two sheets, in between these sheets, we have a magnetic field. Okay, but if we go above this and below this point, so for this one here also it will have a this kind of direction, isn't it, for this sheet? Okay, and for this sheet, this below z is equals to 0 will have this direction. Okay, so in between these sheets there will be a magnetic field, okay, with some direction which will depend on the current density, the direction of the current density. But above these two sheets, the total magnetic field will be 0. So it's a concept. You have to understand, it's a concept. So the concept here is that if there are two sheets with current density opposite to each other, then the magnetic field will be something in between these two sheets, and magnetic field will be equals to 0 outside these two sheets. Okay, so I will repeat what I'm saying. I'm saying that if okay, so see there are two sheets with current density. So if the current density of these two sheets are opposite to each other, are in opposite direction to each other, and have same magnitude but are in opposite direction to each other, then there will be some magnetic field inside these two sheets. Okay, and the magnetic field outside these sheets will be 0. Okay, and if these two sheets have same direction, okay, and same magnitude, then it will have some kind of magnetic field outside these two sheets, and inside these two sheets the magnetic field will be 0. Okay, still not clear? Clear na? Clear. Okay, okay, all right. So got it. So here it will be, the value will be 0. Got this? The value will be 0. Okay, now let's go to question number 4. So question number 4 is, for a diamagnetic material, which of the following is correct? Can someone from you tell me what characteristics a diamagnetic material has, and which of the following is correct? Yeah, okay, very good. Okay. Yes. Okay, okay. So for diamagnetic material, you have to understand that the relative permeability is less than equals to 1. Okay. So here mu r is equals to mu by mu naught. Relative permeability is equals to mu by mu naught. And susceptibility is equals to mu r minus, this is the formula, mu r minus 1. So since we know that for diamagnetic material the relative permeability is less than 1, then our susceptibility will be 1 minus 1, then x. This will be C. Here our mu r is less than equals to 1. So our susceptibility will be less than equals to 1 minus 1 into x. Susceptibility will become less than equals to 0. You get this point? So our here mu r less than 1 and our susceptibility is less than 1. So option B. Less than 0. So option B. Any doubt till here? Okay, let's go ahead then. Consider following statements regarding the boundary between two magnetic medium. Okay, so try to understand this question. This question is concept based. So if you will try to take mental note of this question, and this question will help you a lot conceptually. Okay. So consider following statements regarding the boundary between two magnetic media 1 and 2. So the normal components of B is continuous on the boundary. The normal components of H is continuous on the boundary. The tangential component of B is discontinuous on the boundary. The tangential component of H is continuous on the boundary. So basically here, okay, very good, very good. Let's see if other students also can try to understand. So here two media is given, media 1 and media 2. Okay. So basically we have to try to find out the magnetic B perpendicular, B parallel, H perpendicular, H parallel. We have to try to find out the relation between these two. So if we somehow get that B perpendicular is equals to B1 perpendicular is equals to B2 perpendicular, let's say, I'm just saying, then it will be continuous, and if it is not equal, then it will be discontinuous. Okay. It is. So basically we have to try to find out the relation between perpendicular, parallel, perpendicular, H perpendicular and parallel, B perpendicular and parallel. Okay. And then we will be able to find out what is going on. Okay. So for a magnetic material, our B by mu naught minus M. M here is magnetization. Okay. So the boundary condition for B says that is the boundary condition for B perpendicular says that B1 perpendicular will be equals to B2 perpendicular. Okay. So first thing we got that here the normal components of B, that is B1 perpendicular will be equals to B2 perpendicular. So it will be continuous. So first is correct, right? Let's go for the second one. Second option is B1 parallel. The parallel component of B is equals to B2 parallel plus mu naught K into N. Here N cap. K vector into N cap. K vector here is surface current density at the interface. So B1 parallel will be equal to B2 parallel if the surface current density, that is K, is equals to 0. But if there is a surface current density at the boundary of medium 1 and medium 2, then our B1 parallel will not be equals to B2 parallel, and it will have a formula, it will have a boundary condition something like this. That is B1 parallel equals to B2 parallel plus mu naught K cross N cap. K here is surface current density, N is unit normal to the interface. Okay. Is there any problem till here? Okay. Okay. Now the second concept here. Ha, good. Very good. Okay. Let's go to the second point. The second here point is the boundary condition on H vector. So H vector, boundary condition on H vector is H1 perpendicular minus H2 perpendicular will be not equals to 0. It will be minus magnetization, perpendicular magnetization M1 minus M2 perpendicular. Okay. Another boundary condition is H1 parallel minus H2 parallel will be equals to free surface current density at the interface cross n vector. Okay. So from these equation and these equations, what we got to know here is B perpendicular is continuous across the interface and H parallel and B parallel are discontinuous across the boundary. Discontinuous, why discontinuous? Because it has a, if this boundary has a free surface current density, then it will be discontinuous. Okay, this much we got. So here the normal component of itna H is discontinuous, so this is the wrong statement. The tangential component of B is discontinuous on the boundary. So here the tangential component is discontinuous. So this is correct. The tangential component of H is discontinuous. So this is also correct. So 1, 3 and 4. Yeah. So options here are not given to us. So those option which is given to us is 1 and 4. Yeah, we will put 1 and 4 and or 1 or 3. Okay. Okay. Yeah. See. One second. No, it's saying the tangential component of yeah, see, there is a free surface current density at the interface. So if there is a free surface current density, so it won't be equals to 0. This is not equals to 0. It is not equals to 0. Okay. So tangential component of H and B are discontinuous across the boundary. Okay. Sorry. Yeah, so yes, you are right. This is you are right. This is free surface current density. So free surface current density Kf. So free surface current density here is 0. So since free surface current density is 0, our uh, tangential component of H is continuous on the boundary, and not, it's not discontinuous, it's continuous on the boundary. So option will be only 1 and 3 options are correct. The tangential component of H is continuous. Okay, and it's not yeah. So option A is the correct answer. Okay. Yeah. Now let's go to the question number 6. So question number 6 here says that a circular loop located on x square plus y square is equals to 9 and z is equals to 0 carries a direct current of 10 ampere along phi direction. The ratio of magnitude of H at 0, 0, 0 and 0, 0, minus 4 is. Okay, so it's, this question is simple. A circular loop de rakha hai. It has a radius of 3 at z is equals to 0 and it carries a direct current of 10 amperes along phi direction and ratio of magnitude is asked to us. Okay, so let's go. So x square plus y square is equals to r square is equals to 9. So the radius here given is r is equals to 3, that is radius of the loop. Okay, centered at the origin. Now let's take, so at point P, that is 0, 0, 4, we have a r vector. Okay, r is here small r is the hypotenuse of the height h, and r, that is radius capital R. So the small r will be equals to r square is equals to, will be equal to h square plus r square. This is Pythagoras theorem, simple. So hypotenuse is equals to, hypotenuse square is equals to height square plus base square. So this is what I have written here. For so here field due to infinitesimal like element on the wire, that is field at P, okay, due to the infinitesimal small element dl on the wire will be equals to B will be equals to mu naught. We know this. Db is equals to mu naught upon 4 pi I dl cross r upon r cap upon r square. Here dl cross r, since dl and r are perpendicular to each other, this is equals to dlr. Okay. So for this circular loop from symmetry, we find that the contribution of the horizontal components, that is, see here, let's say we have a db, okay, in this direction. So it will have two components, one horizontal, another vertical. So for this circular loop, there will be like this, like this. So all the horizontal components will cancel and only a vertical component will remain. Okay, the total magnetic field will remain in the vertical direction and all the horizontal components will cancel out. Okay, so here B vector will be equals to mu naught upon 4 pi I by square cos theta dl in z direction from 0 to 2 pi r, from this parameter, sorry, I'm saying parameter, yeah. So the whole circumference. So for this circumference, it will be 0 to 2 pi r dl z. So here cos theta will be equals to r, that is base upon hypotenuse r. Okay, we will solve the question, that is it will be equals to 2 pi mu naught upon 4 pi I by r square r by small r 2 pi r capital in z direction. Then again we will solve it. B will be equals to, instead of r, small r, here we will put the value capital R square plus h square to the power 3 by 2. Okay. Now putting the values, h is equals to 4, r is equals to 3, p is equals to 0, 0, 4 and current I is equals to 10 ampere. Putting all these values, we will find out the value of magnetic field B, which will be equals to 9 mu naught in the direction of z. Okay. Similarly, for point P2, that is at the coordinate 0, 0, minus 4, h will be our minus 4, rest will be same. So for B2 also it will be equals to B2, since here in the it's a h square. So it does not matter if it's in a positive h direction or negative h direction. It will be h square, which will be equals to 9 mu naught z. So it will be equal to B1 and B2 will be equal. So ratio has been asked to us. So ratio will be B1 upon B2, which will be equals to 1. Okay. Is there any problem you have till here? Okay. Okay. Let's go ahead then. Question number 7. Given the magnetic vector potential, A is equals to minus rho square upon 4Az Webers per meter. The total magnetic flux crossing the surface phi is equals to pi by 2, comma phi is in between 1 to 2 m 2 meters and z is between 0 to 5 meters, is in Webers we have to find out. Okay. So here magnetic vector potential is given to us and total magnetic flux crossing the surface is asked to us. Okay. So here four. So let's make the surface that has been asked to us. So the surface here, this is in cylindrical coordinate. Okay. So 0 to 5 meters we have from z is equals to 0 to z is equals to 5 meters. This is 5. Okay. And this is 0. Huh? And our rho is from 1 to 2 meters. So in if we write it in x and y, if we convert it into Cartesian coordinates, here it will be 1 and here it will be 2. Okay. Another thing is phi is equals to pi by 2. So yeah, so in y direction it will be 1 to 2. If we will convert, phi is equals to pi by 2 and rho from 1 to 2. Okay, we convert into x, y and z Cartesian coordinates, we get this. We get a rectangle with in a yz plane with from with y is equals to 1 to 2 and z is equals to 0 to 5. Okay. Alright. Yeah. Here vector potential is given to us. A is equals to minus rho square upon 4. Okay. So our B will be V cross A vector. That is magnetic flux through surface area S. This is the whole surface area. This is whole surface area. Okay. So magnetic flux will be equals to B dot dA for a whole surface area S. Okay. Do you have any problem till here? This is simple formula. Yeah. Ha. Yes, exactly. Sim Similarly, B will be equals to curl of A. That is magnetic vector potential A. So curl of A will be B vector. Okay, this is also a formula. So curl of A dot dA for the whole surface area S. Now from here we can using Stokes theorem, from here we can go to A dot dA. Okay. So L here is parameter of S. So now this L, instead of a whole rectangle, we will break it into L1, L2, L3 and L4. Okay, L1, L2, L3 and L4. So let's break it. Let's break this whole uh, surface, this whole closed loop into L1, L2, L3 and L4. So A dot dl, L1, A dot. So here till here do you have any problem? Oh, okay, let's go ahead. So we have just broken the whole L is equals to parameter of S, and then we have broken it into this. Now integral over L2 and L4 will be 0 since A is perpendicular to DL. So integral over L1, sorry, integral over L2 and L4 will be equals to 0, and we have to only find the integral over L1 and L3. Why? Because, sorry, why? Because here our A vector is perpendicular to DL. A vector is perpendicular to DL. So L2, for the components of L2 and L4 we have a 0 because it's A dot DL. So if they are perpendicular to each other, then the whole component will become 0. So only phi will be equals to L1 and L3. For L1 and L3, let's put the value of A, which is minus rho square by 4 minus rho square by 4 dz. Okay. Now let's put the value of rho. So rho for L1 will be, rho for L1 will be 2, rho for L3 will be 1. So let's put those values here. Okay, and we will solve this equation. Alright, and we will get this. The flux crossing the surface will be phi is equals to minus 3.75 Webers. Okay, simple integration it is with the values. So minus 3.75 Webers. Okay, is there any problem you have? Any doubt? Okay. Okay. Let's go ahead then. Given that h1 is equals to h1 is equals to this minus 2ax plus 6ay plus 4az amperes per meter in region x y minus z minus 2 less than or equals to 0, where mu1 is equals to 5 mu naught. The B2 in the region y minus x minus 2 greater than 0, where mu naught is 2 mu naught is mu2 is equals to 2 mu naught is. So here, okay, now our interface is not z is equals to 0 or something. It has a proper function. The function here is y is equals to, sorry, our function here is y is equals to x plus 2. So the interface between the z region in the plane given by function of x comma y comma z is y minus x minus 2 is equals to 0. So first let's try to find out the unit normal for the plane. So the unit normal for the plane will be vector of del vector of f upon mod of f, that will be equals to minus x cap plus y cap upon under root 2. Okay, so we have simply put these values and then the magnitude of this. So h1 is given to us. H1 is minus 2x plus 6ay plus 4az. H1 is given to us, mu1 is given to us, and mu2 is given to us. So now how to find out B2? So for B2, interface is given to us, a region is given to us, and we know the boundary conditions. So first H1 perpendicular will be equals to H1 vector dot n cap in the direction of n cap, in the direction of normal vector of the interface unit normal. Okay. So now H1 dot n cap. So we know the H1 vector, we know the n cap, the unit vector. Can we find out H1 dot n? Yeah, yes. So we got it, and then we got the H1 perpendicular, which will be equals to minus 4x plus 4y. Similarly, H1 perpendicular will be, parallel will be equals to H1 minus H1 perpendicular. So we know the value of H1 perpendicular, we know the value of total H. Can we find out the value of H parallel, H1 parallel? Yes, which will be equals to total H1 minus perpendicular H1. It will be equals to this. Now since there is no surface current at the interface, our H1 parallel will be equals to H2 parallel. Okay. This means that H2 parallel will become this. We have find out the value of H1 parallel, isn't it? Which will be equal, it will be equals to H2 parallel. Also, we know the boundary conditions which says that B1 perpendicular is equals to B2 perpendicular. We will put the values, that is mu1 H1 perpendicular, mu2 H2 perpendicular. We will find out the H2 perpendicular. So total H2 will become, now we know H2 perpendicular, we know H2 parallel. So total H2 vector will be H2 perpendicular plus H2 parallel. So simple arithmetics it is, simple subtraction, addition, that's what it is. So we got H2. Now since we got the total H2, B2 vector will be equals to mu2 into H2. So we know the H2 value, we know the mu2 value, we will put it here and we will get the total B2. Okay, it's simple. We know the boundary conditions, we know the values, we have to just put these values and the boundary condition, apply the boundary conditions, and we will get the total B2. Do you have any doubt here? Okay, alright, let's go ahead. Okay, so now consider following fields. So first field is given to us, second field and third field is given to us. Which one of the above field represents magnetic field? Okay, so some fields are given to us and now it's asking us to identify which one will be the magnetic field. So can you tell me how to solve this question? Okay, no problem. So for magnetic field, the divergence of the magnetic field if the divergence of the magnetic field is 0, okay, and then we go and then we find out the curl of the magnetic field. If the curl of the magnetic field is not equals to 0 and the divergence of the magnetic field is equals to 0, divergence of the field is equals to, once again, let me reframe my sentence. If the divergence of a field is equals to 0 and if the curl of that field is not equals to 0, then that field is no will be representing magnetic field, okay. And if the field's divergence is not equals to 0, then it won't be representing magnetic field, okay. मतलब कि अगर कोई फील्ड है, ठीक है, तो अगर फील्ड को हमें आइडेंटिफाई करना है कि वो मैग्नेटिक फील्ड है कि नहीं, उसके लिए सबसे पहले हम उसका डाइवर्जेंस निकालेंगे, ठीक है। डाइवर्जेंस निकाला और दैट इज इक्वल्स टू 0, फिर हम उस फील्ड का कर्ल निकालेंगे। अगर वो कर्ल, उस फील्ड का कर्ल इज नॉट इक्वल्स टू 0, तब हम कह सकते हैं कि वो जो फील्ड है वो मैग्नेटिक फील्ड है, ओके। तो हम इन तीनों का सेम चीज करेंगे। Okay, field 1 हमें दे रहा, it's field 1 is given to us, okay। First we will try to find out the divergence of the field. Here we find out the divergence of the field, it is equals to 0. Then we will go for the next step, which is we will try to find out the curl of the field. So the curl of the field we found out, it is not equals to 0. So similarly we will do the same divergence and curl for the field number 2 and field number 3. We will find out that for both the fields, for all these three fields, that divergence is equals to 0 and the curl is not equals to 0. So here all the three fields represent magnetic field. Okay, so all the three represents magnetic field. So option A is the correct option. Alright, any doubt? Okay. This is the property of a magnetic field. So property of magnetic field is divergence of the magnetic field will be equals to 0 and curl of the magnetic field will be not equals to 0. Okay. This is the characteristic of magnetic field. Hello. No, I'm not getting. Hmm. Still, uh, I'm not get, I'm not getting your question. You can, maybe you can post it in the properly. You can post it in the question forum that we have, so that I can take it what you are asking. Okay. All right. Okay. Let's go ahead then. Okay, so question number 10 is a very long solenoid 2 cross 2 centimeter cross section has an iron core. Mu r is equals to 1000 and 4000 turns per meter. If it carries a current of 500 milliamperes, then the energy per meter stored in its field is. So we have to find out. A solenoid is given to us, a long solenoid with a cross section of 2 cross 2 centimeters. Okay, it has a iron core with mu r is equals to 100. Sorry, 1000. Mu r is equals to 1000 and it has 400 turns per meter. Okay. and current 500 milliampere current is flowing into it. So energy per meter is asked to us. Okay, so we know that magnetic field inside a long solenoid will be equals to mu naught Ni away from the ends. If we go infinitely away from the ends, then B is equals to mu Ni. Okay, mu Ni. So mu will be mu r mu naught Ni. Here N is number of turns per unit length and I is the current in the coil. This is the formula for a solenoid. Okay, magnetic field formula for a solenoid. So magnetic flux through its cross section will be equals to B dot A. Alright. So B dot A, here we will put it in here. It will be equals to mu r mu naught Nia. Now here you see n square. N square I have written because in a per unit length there are n number of turns. So the total magnetic flux will be for that total number of turns. Okay, so in a unit length, if let's say there are n number of turns, then our total flux will become B dot A, which will be equals to mu r mu naught Nia dot into n number of turns n. Okay, so our phi total phi will be this. Now self inductance is equals to total magnetic flux upon current. So our self inductance will become mu r mu naught n square I A. Now the energy per unit length is equals to half Li square. So half Li square will be half Li. Put all the values of L and we will find out this. Now put all this is equals to E. E is the energy stored per unit length. Now put all the values of N, I, A and we will get the value of E. So the value of E will be 1.005 joules per meter. And the question is asked in joules per meter. Okay, it's a simple formula based question. So is there any issue? Any doubt? First formula is, yeah. So simple. So the energy stored in a solenoid will be proportional to mu r mu naught the square of total number of turns per unit length, area of the cross section area and the current flowing through it, the square of the current flowing through it. So got it? The energy in a solenoid will be proportional to the n square, I square and mu r mu naught A. Alright? Okay. Okay. Is there any other doubt you have? No. Okay. I will stop sharing that. Uh, yeah. Okay. So we have solved 10 questions today. And if you have any doubt, you can put it in my comment section in the YouTube. And if you were asking some question, Arun Raj, I think I can take that question again. Yes. Hmm. 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 Yes. How to think. Yeah. Hmm. Hmm. So this happens. Actually, this happens. This subject is very tough. Okay, so don't worry that you are not able to think in the first attempt only. So don't worry about that, because there are certain set of questions. So once you have practiced it, then you will be able to think on those levels. Those, so don't think that oh, you can't solve this question, you have to think in a this particular direction to solve this question. It's all right, this subject is tough. So if you can't think, then you and you, if you are thinking that you are giving 100% in this subject and still you are not able to think in certain way, then it's okay, nobody will be able to think that. Even if someone is very, there might be some cases where they might think exceptionally well, but most of the students won't be able to think like that. So the thing that what happens is these kind of questions have a set pattern. Okay, so once you solve these, once you get to know, okay, this how this is the way you have to think, once you will be able to and think in that, once you get the solution and get the nudge in that direction, once you do that, after that you will be able to flawlessly solve these questions. So this needs practice, a lot of practice. Okay. Yes. Hmm. Hmm. Yes. Yeah. Okay. So practicing, that's what makes a man perfect. So you have to practice as many questions as you can. Do one thing, you start practicing the gate questions. So if you practice those previous year gate questions now, that would be really good for you. Do can you know, can may I know in what profession you are? Hmm. Hmm. Yeah. So okay, so do one thing. If you want to really get into the problems, how to problem solve. So these are a, I told you, like these are a set, these questions have a set pattern. So boundary condition will be there, then Biot-Savart's law, Ampere law, then characteristics of magnetic field or electric field. So something like this, the question will be. So do one thing. If you really want to go into depth, not concept wise, because concept wise NPTEL is there and you are yourself a teacher, so concept wise you don't have any problem. So do one thing, if you want to solve numerical problems, you solve the gate problems. You go for the previous year gate questions, and then these assignments will be really easy for you. They won't be that tough. It will be the first step, just first step. So solve the gate previous year questions. Hi. Hi. Yes. Hmm. Yeah, so before solving these assignments, now go for this gate previous year. Even if you don't solve them. Just read them. Just if you read them, then you will know the set pattern. Okay, so this kind of question needs this kind of. This is the way to go. So there will be set patterns, and once you solve these gate questions, now then it will be really easy to solve these assignments. Okay. Okay, all right. So all the best for the assignments, and I hope my session helps you. Okay, all the best. Bye bye. Yeah, you have. Mm-hmm. Hmm. 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 Yeah. Hmm. Hmm. I get it. I get it. I will ask him to change, edit it a little bit. Edit the audio. That way. Okay. Chalo. Okay. Bye. All the best for assignment 5. Bye.